Okay.
Little diffusion never hurt anybody. Okay. So let me write down some of these key functions again, just to orient us, and then we'll talk about this real quick for these primitives for the 1D spherical case, and then we'll start talking about gravitational waves. Now I'm planning 2 lectures on gravitational waves. And of course, we talked on Tuesday that LIGO's detected a binary black hole merger already in O3. So, you know, the beat goes on.
Should detect them like every week.
That was I think the upper end of like the estimate for O3 is like once a week.
Yeah.
First week.
Then their
Bam.
large range for neutron star mergers were 1 to 30 something.
Yeah, yeah. Some number of detections per week. Okay, so
I think that's for the whole cycle, for the 1 to 30.
Yeah, it is for the whole observing run. It's 1 to 30. Oh, there we go. Okay, so just to remind ourselves of our metric, minus the lapse, which is a function of radius and time squared, dt squared, plus this function x, which is a function of space and time, squared dr squared, and then our r squared d omega squared. And in this, the lapse is e to the phi, which is a function of space and time. And this function x is, looks a lot like our function that we have in short shield. Enclosed mass, gravitational mass, divided by the radius to the -1/2, like that. And then when we rinse through in this case, we did the radial gauge and the polar slicing. And then from the Hamiltonian constraint, we get mass as a function of radius and time is equal to, the one I want to write down, it is 4 pi integral from 0 to the radius that you're evaluating at, rest mass density, enthalpy, Lorentz factor squared minus the pressure, r prime squared dr prime. So just integrating that. And then our metric potential, B, space and time, is going to be equal to, r, of course. Integral from 0 to r of this function x squared, all times mass enclosed r prime of t, all over r prime squared, plus 4 pi r prime squared times rho naught h Lorentz factor squared v squared plus the pressure, close, close, dr prime plus r initial, it doesn't have a prime, the initial metric potential, which we get from the boundary condition by matching the short shield. The short shield metric on the exterior is where we get that from. So we can solve for that like that. And that's our phi naught. Okay. That's in the notes. I'm not going to write that down again. Okay, so now let's talk about, in this metric, this is the part that I didn't get to last time, how do we actually evolve matter with this gauge and slicing condition in spherical symmetry? Well, as usual, I'm going to switch to Muse and News. I think, did I do that last time? Yeah. Okay. Gradient of the stress energy tensor equals 0. What do we call this? Ish, conservation of form momentum. For momentum conservation. Now, what's this one? Conservation of mass current, continuity equation, baryon number conservation, take your pick. All right, and we're going to do the usual thing using what we used when we did the full GR in 3D, the Valencia formulation in flux conservative form, where we have a partial derivative of some solution vector. And in spherical symmetry, I'm going to go ahead and add these geometric factors, and I'm going to reduce to spherical symmetry. So we have 1 over r squared, partial with respect to r of alpha, r squared over the x times some flux vector is equal to some source vector. So here I give these geometric factors because I'm taking a divergence in spherical coordinates. Right. All right, and now my solution vector. I think I'm going to write it in a way that I usually don't, but here we go. So my solution vector is going to be the following. It's going to be D, which is equal to alpha x. That's cut off for me in my notes. That's got to be a J. Yeah, of course. So that's basically the density, and that's equal to x rho naught Lorentz factor. Pretty easy. Okay. I think I'll write this in a more verbose way. All right, and then the next one, I'm going to leave that one out. So there's a way to write down the advection equations for a mass scalar as well, but since we don't need that for what we're doing. We don't need that for what we're doing. I'm going to leave that out. The momentum, the r component of the momentum is alpha x t tr. That's that component of the stress energy tensor. We're using stress energy tensor for a perfect fluid here, right? And so just substituting in what I know that to be, it's rho naught enthalpy Lorentz factor squared times the spatial velocity. And then finally, our energy variable is alpha squared t minus d, because we just want the energy, we want the mass energy taken away from that, so that we're not doing the total mass energy there. And that's rho naught h w squared minus p minus d. So those are my conserved variables, right? And so the primitives are the rest mass density, enthalpy, spatial velocity, and the pressure.
Do we have to track the enthalpy separately? Because you can derive that in terms of the other scheme.
Yes, but the enthalpy also includes the internal energy. So however you cut it, it's one extra variable. You don't have to track the enthalpy by itself, but if you don't, you have to track the internal energy.
You need an equation of state.
You need an equation of state.
Yeah, okay.
Yeah. Yeah.
Because you can't, from the, you can't do that. Not in this case. Like you're telling you, you can just get the internal energy from the energy equation, or from the conservative. Okay, that you can't do.
Not here. All right, and now our fluxes. Okay, so that's our vector of conserved variables. Now I'll write the fluxes in a somewhat more compact notation, I think. So this is going to be dv, cool. Ignore that. SR v plus p, cool. SR minus dv, transpose. So there's the fluxes when you modify fluxes.py. These are the fluxes of these conserved variables as we define them there. Okay? And then our source terms, source vector is going to be equal to, let's see, first one, 0. There's no, for the mass equation, there's nothing. Now for the momentum equation, there's something, and it is something. SR V minus tau minus D, all times alpha x, all times 8 pi r p, the pressure, plus mass over r squared, that's mass enclosed, plus alpha p x m over r squared, plus 2 alpha p over x r. Energy, 0. And so these terms that have, pi's and r's in them are from the geometry, from the spherical geometry.
So you already explicitly included those
It's,
in the.
that's right.
Okay.
Well, no, you still need this out here,
Yeah.
and you still need this here. So what I've written here as the flux and here, right? The flux, looking at it, doesn't have any geometry terms in it, right? So that goes in there. And the geometry for this divergence is accounted for here and here.
Yeah.
Right? But the source term, when you switch coordinates, you incur an additional source term on the right-hand side to account for the change in the coordinates in different locations in space. And it comes in like a source term.
How do we, what about r equals 0 in the master?
Don't go to r equals 0.
Does it go up or does it?
Yeah, no, I think it blows up. There's nothing that cancels that out.
You can expand out that term of the flux in it. Take everything that's not the derivative of the flux over to the right-hand side. As a source.
But this partial is on the outside.
But yeah, you
Right.
you propagate that through, then
Yeah.
you'll have partial of alpha r squared over x just times the flux.
Mm-hmm.
That can go to the other side then because you're no
Mhm.
longer taking the derivative of the flux. So that could also be included in the source term, and then you
Could
can
be.
conservative form, just dtu.
But then you would have spatial gradients on the right-hand sides.
Oh.
Because alpha and x are still dependent on space.
Yeah.
And the way we like to write it down, it's not always the case that we do it this way, but we like to avoid derivatives in our right-hand sides. Spatial derivatives, at least. You can stick it into that flux divergence. So that's the 1D set of equations in spherical coordinates. Eric,
Can you move the computer over? I'm not used to this thing.
sorry. I'm not used to writing this far over on the board, but that source term is a beast. You see it now?
Yeah, no, it's quite glory.
Hmm?
No, it's core glory.
Mm. Okay. And I've posted these notes now up on the website, so you can get to them there. Again, this is also O'Connor and Ott 2010. It's all there in case I've made a mistake in the notation somewhere. Okay. And one of the things that we're interested in GR numerical relativity is gravitational waves, obviously, from so many different aspects. But when we do one of these simulations, one of the things we haven't talked about so far is, well, how do we get the gravitational waves out? If I want to make predictions for what the gravitational wave signal is from some astrophysical system, whatever that system happens to be, how do I make estimates for that? Where is that information encoded, and how do I extract it from a numerical relativity simulation? So we're going to talk about that a little bit. Today, I'm going to just introduce a common approach, which is approximate, but will look familiar to some people based on just the mass quadrupole. So we're going to do a couple lectures on gravitational waves. So I'm not going to get into a whole lot of this today. I do encourage you to go read chapter 9. In particular, I doubt I will have a lot of time in class just with 2 lectures to talk about the details of the detector side of things, which are just really cool, but I'm no expert in for sure. Expert in most of this, not really, in my opinion. So you can read that. I think it's interesting. But I'll talk about a little bit more of the stuff on the side of actually simulating this stuff and how we make connection with the gravitational wave predictions from that side of things. So I already introduced gravitational waves way back when we were in chapter 1. We talked about this in the weak field limit. And so some of those derivations that I did where we started from the weak field limit and got to the wave equation, go look at your notes. It's in there, so I'm not going to redo that. I'll just refresh us on what the basic gist of that was. So we'll take this weak field limit and remind yourself that what that means is that I express my metric, my 4 metric, as the flat metric, oops, about to switch to alphas and betas, plus a metric perturbation, this HAV, where the magnitude of HAV is much, much less than 1. So it's small. So the space-time is almost flat. So we call that the weak field limit. And then we're going to have the, I'll show you why we do this in a second, the trace reversed metric perturbation. And what that is, we're going to put a bar on our metric perturbation. We're going to define this as the metric perturbation minus 1/2 flat metric eta AB times HCC. So the trace, right? This flat metric, we call this the trace reversed metric perturbation. And now we can choose our gauge to make constraints on this. So the goal here is to get at, we know what the flat metric is, so what we really need to solve for is what the metric perturbation is, given some stress energy tensor or something like that, or some initial perturbation. Okay, so now we need to choose a gauge. So we've got to constrain all the various components of HAV. And the way that we've always done that is to pick gauges or provide equations to solve for it. And so let's choose the Lorentz gauge because it's convenient for lots of reasons. And in that gauge, remind yourself that del of A bar, H bar, AB, is equal to 0. Okay? And once you do this, and this is what we did way back in chapter 1 to get the wave equation. And so doing that does give you a wave equations. So then the field equations become the following. The Ambertian operator, H bar AB, which we define as grad upstairs C, grad downstairs C of H bar AB equals 0. And this, the Ambertian is a 4D Laplacian, right? And this is a vacuum wave equation, right? Laplacian is something equals 0, so it's just a wave equation, right, in 4D. Specifically in vacuum, because we haven't included any interaction of the waves with matter, which matter causes refraction, et cetera, and it can do this. So still, H bar AB is not uniquely defined. We can keep playing this gauge transformation game. We can keep adding some gradient of a scalar field to it, right? And the whole Lorentz idea. We can do that ad nauseum. So we haven't uniquely identified the components of H bar AB. And so we need additional constraints. We need to make some more choices. And the one that is most commonly made is to apply what's called the transverse traceless gauge. That's a Q, not a G. All right, and so what that means is that the following, H bar A0, and now in the transverse traceless gauge, I'm going to denote that by 2 little capital T's there. Those are not indices. Those just mean it's transverse traceless is equal to 0. Okay, so that means that the only non-zero components of this h bar AB are purely spatial. So I'm getting rid of the time components and making this purely spatial. Okay, and then the other thing that we're going to do in transverse traceless, h bar, t, downstairs A, upstairs A equals 0. Now, A's are indices, so I'm taking a trace there. Right? Traceless, right? Transverse, traceless. Transverse, traceless. Purely spatial, traceless. Cool. Okay. So that's my next gauge choice, which eliminates some of the free components, specifies some of the free components. Okay. This implies, actually, that my original metric perturbation must also be traceless. And therefore, in this particular gauge, once I've made things transverse and traceless, look at how I've defined the h bar, the trace reverse perturbation. I'm subtracting off something that goes like the trace. And so if there is no trace, h bar AB is equal to h AB. So you see why we make these assumptions. We make these gauge choices because now I can solve directly for the thing that I want, which is the metric perturbation. Okay? So the transverse traceless components then of the Riemann tensor are the following. Now we're going to deal with the 40 Riemann tensor, and you can go check this out. I won't reproduce the equation for calculating it. But I0, J0, so I'm taking time components in the second and fourth index of the Riemann tensor, is minus 1/2 of H double dot transverse traceless IJ, where this is the second time derivative. That's what the double dot represents. So now I've related the Riemann tensor, which is a fundamental property of the curvature of the space-time, right? That's the thing that really characterizes how curved space is, to this transverse traceless metric perturbation in the weak field limit, specifically a second time derivative of it. Okay? Now, so Lorentz plus transverse traceless gives us 8 out of 10 of the free components. Of HAB. So we've got 2 unspecified components at this point that are still free. Anyone know what those are?
Polarization.
Yeah, that's right. So there's 2 different polarizations for a gravitational wave, just like an electromagnetic wave, right? And so those are the polarization states. Okay. Gives us +2, and then we're good. But we got to account for both of those polarization states because the waves can be polarized. That's a physical freedom. Okay. So here we're going to introduce polarization tensors. Two of them. And they're going to look like this. In Cartesian coordinates, I will specify this. So, so these 2 things in general are just E plus and E cross AB. That's the general form for the polarization tensors. If I reduce this and I take a basis and I take a Cartesian basis, these are pretty simple, and so I'll write this down. E plus XX is equal to minus E plus y, y is equal to 1. And then similarly, E cross x, x, y is equal to E cross x, y, x, which is equal to 1 in a Cartesian basis. So the xx is the negative of the yy for plus, and the xy and yx components are symmetric for the cross, equal to 1. All other components of these tensors are 0 in a Cartesian basis. All others equal to 0 in the Cartesian basis. It's fairly simple. Sorry, I got bunched up down there. Can you read that? You can at least hear my words. Okay. All right. Then my gravitational wave is specified by, please turn to the page, the spatial components of the transverse traceless metric perturbation. And taking into account the polarization, I'm going to introduce some polarization amplitudes H plus, E plus, IJ. That has got to be a mistake. These indices don't make sense. That's a scalar. Just call that JK. As my son likes to say a lot, just kidding. JK. And H plus, H cross are dimensionless amplitudes. The waves. Like that. So I've got, this book's got a nice image, right? But I,
much more than
huh?
much more than
What?
H, the H's
Yeah.
are much smaller than 1.
Yes, 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 absolutely. Yes. If they're not, we're in the strong field limit. Yep, that's right. Sorry, I was thinking about how to represent this polarization. And so these waves, they do this, right? And so if you think about a wave coming at you, right? And here, right down there, there were no z components. And so I'm assuming that the wave is propagating in the z direction, okay? So what's going on is if this is the z direction and this is the wave, it's doing this as it's going along. Or it's doing this. Make it go by 90 degrees, or I'm sorry, 45 degrees. And there's the cross polarization. So those are the two polarization states of these waves as they propagate along. Copy and pasted picture in the notes. Not as good as my interpretive dance, though. Okay. And so we can represent a traveling wave by this metric perturbation in terms of its two polarization states and the amplitudes of those polarization states. All right. So now, what does a GW wave, a gravitational wave, do to two test particles? So let's say we just put two massless test particles separated from each other by some known separation, and a gravitational wave passes through those two particles. So two test particles with separation initially. And I'm going to call it xc of I, right? Some vector separation between these two test particles, xc. The effect of the passing gravitational wave is to excite a xc double dot, an acceleration. And that is expressed as 1/2 times the double dot of the transverse traceless spatial components of the metric perturbation times exceed J. So this acceleration of the separation between these two test particles is characterized by this metric perturbation, the second time derivative of the metric perturbation. And that comes from the geodesic equation, if you wanted to derive that on your own, have fun with it. But it comes from the geodesic equation. You just plug that in with the metric that we've selected here and compute that, okay? And so the passing of a gravitational wave changes the separation between these two massless test particles just because a gravitational wave went through, okay? And what we can do with that, if it's causing some separation, it's causing some strain. We can define a strain between those two particles. So we can say that the relative strain induced by the gravitational wave between these two particles is delta xc over xc, because it's relative, okay? So how much does that separation change? And just by looking at this equation, we can deduce that that is proportional to the transverse traceless metric perturbation. It's directly proportional to it, just by working out that very simple integral, right? And so this strain, this is a strain, proportional to the metric perturbation. And so you will see often in the literature that H called the strain. When we plot it in our paper, we call it H. What do we call it in the paper? The strain. Technically, it's the transverse traceless metric perturbation. But who wants to say that? Nobody wants to say that. That's a lot of words. You pay by the word in a paper. Strain. Okay? And so we often just call this the strain because it's directly proportional to the strain between two test particles. What does this mean? This means that the distance between locations in space are changing, right? Between two test particles which are on geodesics. So they're not accelerating with anything except free fall, right? They're following geodesics. And so sort of the distance between neighboring geodesics is changing, right? And that's what LIGO measures, right? How much does the distance of this laser beam change in time? Okay. So let's do the following. Let's take the weak field limit, weak field slow velocity limit. So we are essentially Newtonian, okay? Weak field slow velocity, not special relativistic speeds, not general relativistic gravity. And let's write down an equation which is horribly mangled by the print job here. So bear with me. H bar AB, which is equal to grad C upstairs, grad C downstairs, HAB, which is equal to minus 16 pi stress energy tensor AB, okay? We can solve this equation. So I've introduced some stress energy tensor where now I've got sources. I've got some matter source or some energy source in my gravitational field, okay? Because now I have a non-zero stress energy tensor. And I want to solve this equation. So now, right, before we had this equal to 0. That's a wave equation. Write down the solution immediately. Well, you can still write down the equation, the solution for this, right? We do it all the time, you know, when we're solving Laplacian equations or Poisson equations. This is now a Poisson equation, not a Laplace equation. Operator is the same though. And so you go and you look in Abramovitz and Stegen and you find the appropriate Green's function and you write down the solution. And you never do the integral yourself. And so if you do that, you find that H bar AB as a function of time and position x is equal to 4 times the integral, a volume integral, spatial volume integral of this stress energy tensor multiplied by t minus the absolute value of xi minus xi prime. I'm going to need to erase. It's big. As a function of, this is the time that goes into my time-dependent stress energy tensor. This is a retarded time, right? X prime I, right? So a function of a retarded time and space goes into my stress energy tensor, divided by the absolute value of xi minus x prime I. You recognize this Green's function, right? For the Poisson equation with source terms. That's just the Green's function that you use to solve it. Okay? Okay. So now, let's try to solve this thing. Because again, we care about how matter sources actually give rise to gravitational waves, right? They don't just appear in vacuum. What we did before, where we set it all equal to 0, that was for the propagation of a wave, but we didn't understand where that wave came from. What generated that wave? Here, we have a source term to generate waves, right? It's coming from the matter. Yes, question?
Yeah, so the weak field is also for the source term.
Correct.
In the
That's right.
whole.
Correct. Yeah. And so TAB has to be relatively small as well, relative to 1. Right. Okay. Great. So if we go and take the limit of a distant source. So I'm not very close to the source. Whatever is giving me TAB, right? Whatever is giving me non-zero TAB, put that really far away. I want to sit in vacuum. The stuff is over there, and I want to know what the gravitational waves from that stuff are to a distant observer. In that case, I can expand the integral in powers, right? We're just going to do a Taylor series expansion of x prime I over r, because that gets very small for very large r, right? Which is my distance. This is the distance. Did I define that anywhere? R the distance, right? Distance to the source. So in that case, I can expand, that's a small quantity. And what I get is h bar ij, reducing only to the spatial components now of the metric perturbation. Time and space, xi, is equal to 4 times the integral in my space of TAB as a function of time minus the absolute value of xi minus x prime I, absolute value, and x prime I, all divided by, I'm writing the same integral again, I'm sorry. Sorry. We do this so that we can get rid of this nasty thing, right? Because whenever you're integrating this Green's function, it's this part down here that gives you trouble, right? Because that can go singular. So we do this to get rid of that. And that is reflective that if you were close to the source of the gravitational waves, the sort of assumptions of the weak field don't apply anymore. The metric perturbation might actually be large, close to the source, right? And so that's why we're doing this, to get rid of that tricky part in the integral. Sorry. Again, only the spatial components now, Tij. We get time minus r, that's our retarded time, x prime k. I switched indices here for no reason except to represent this as the spatial part. Okay. So now we're going to make 3 assumptions. 1, we're going to use the virial theorem. Some of you are in the cosmology class. Question?
Do we need expansion terms, or did that just go away?
We dropped the higher order terms.
Oh, we just did.
We just dropped them. We just lit leading order. We just did leading order. We're really far away from the source. Like infinitely far. Okay, and so that virial theorem gives me a way to express this integral of the stress energy tensor. And the tensorial virial theorem looks something like this. D cubed x prime of Tij, upstairs, that probably matters. Let me write this below so that I'm not getting too bunched up over here. Integral of, in space, of Tij is equal to 1/2 the second time derivative of the integral of, in space, d cubed x prime, the time component of the stress energy tensor times space x prime I, x prime j. This is the second moment, the second spatial moment of the time component of the stress energy tensor. The second time derivative of that is equal to the volume integral of the stress energy tensor. That's the virial theorem. I'm balancing kinetic and potential energies, essentially, represented by this. Okay? Cool. So that's relationship 1 that we're going to use. Relationship 2 that we can use is in the Newtonian limit, the time component of the stress energy tensor is what? Make you tell me. The Newtonian limit. Things are moving slow, things aren't very hot. Rest mass density. Right? And relativistically, it's the full mass energy density. But if the energy is small, it's mostly just mass. So there we go. And then we have the third relationship, which is the second moment of the mass distribution. I'm going to call that I. Ij, which is a function of time, and it's going to be defined as the integral in volume of the mass, rest mass density, which is a function of time and space, times time, like that. Prime, right? I'm integrating over this volume. So this is the second moment of the mass. Over here, I had a second moment of the time component of the stress energy tensor, which I said was mass. Okay, you see where I'm going with this, right? I'm going to relate this to some second time derivatives here. Okay, so now 1 plus 2 plus 3 put all together into my expression for this thing here. Give me the following. H bar Ij as a function of time and space is equal to 2 divided by radius, the second moment double dot Ij time minus radius. Easy peasy. And that's my retarded time again. Okay, so now we can go further with this. We have time. What's that left? There's a lot of squiggly eyes in here. I think I'll save that for next time. We will get through this next time though, because this part's important. But I don't want to rush it then. Okay, so now we have an expression for the metric perturbation based on just the mass distribution, right? And we're going to take it one step further next time and relate this to the quadrupole moment of the matter distribution. And then that's a common way of extracting gravitational waves, or estimating really the gravitational wave radiation from some matter distribution. And that's time dependent, obviously, because it has second derivatives in time. And I'll complete that next time. Questions? And I got through a page. All right, cool. Good work so far on the coding stuff. That's great to see progress there. Keep it up.